Hey everyone, welcome to another episode of the Whiteboard session. Today we have with us Sean Bo, one of the key people behind Zcash, the original design, as well as all the upgrades since then. It's great to have you here, Sean.
Yeah, it's awesome.
Yeah, okay. Okay, so let's dive right in. Sean, can you give us an overview of how Zcash works, and then we can, dive into the specific topics of how. Yeah.
Yeah, sure. So I can explain. So Zcash comes from this academic paper from like more than 10 years ago, or roughly, called Zero Cash. And Zero Cash was trying to think about how do we get private payments like in Bitcoin, or payments like in Bitcoin and cryptocurrency, but completely private. And private means that, at least from the perspective of the Zero Cash paper that introduced these concepts, is that transactions should be as indistinguishable from each other as possible.
Mm-hmm.
So whatever value a transaction is spending should be as indistinguishable as any other transaction. So you can't really exclude or do set exclusion tax or whatever. And also, the values obviously can't be public, or any other details about the transaction that would let you to violate anyone's privacy. Depending on who you talk to, it's you can kind of see it as maybe the transaction's encrypted, and you don't decrypt it for anyone, but you use zero knowledge proof to demonstrate that the encrypted version of the transaction is valid, and that's it, really. The exact model, I'll use the whiteboard because we're here.
Yes.
The exact model, the way it works is we have this accumulator. It doesn't really matter how it works for our purposes. I'll just call it accumulator. And whenever we send somebody money, we create something called a note. And again, I'm simplifying things a little bit because this spans almost a decade of development. But basically, a note is a public key, kind of like in Bitcoin, and a value. So you would call this like in Bitcoin, you call it a UTXO. And you have this note, and then you have this thing called a note commitment.
Mm-hmm.
And the note commitment has some randomness or whatever that blinds it so that you can't, so that it can't be, you can't get any information about the PK and V that's hidden inside the note. Yet it's also binding because you can reveal the note data and the randomness to reconstruct the commitment. So when you created some value, send some money to somebody in this protocol, you create the note and the note commitment in a zero knowledge proof. And the network will go and take the commitment and put it in this accumulator. Then later, when you want to spend it, there's another thing. So we'll call this the note accumulator. And then you could call this maybe the spend accumulator.
Okay.
And in this, when we go to spend this note, there's also some other information in here. Again, I'm oversimplifying, but maybe we have some row or some data in there. It doesn't really matter. The actual technical way that it works has to defeat a bunch of different attacks, so it's more complicated than this. But when I spend this note, I reveal a zero knowledge proof. There's a witness into this accumulator that tells me, tells everyone that I know that a note exists. And I reveal something that allows everyone to see that I spent it. Some deterministic computation of this commitment. We call that a nullifier. And this nullifier, it could just be this row value, but that's not secure. It's something that's determined by the node and the row value and everything else. It's some function of the commitment, or is the data in the commitment, or something to do with the node commitment.
I see.
And we reveal it, and it's just, from everyone else's perspective, it's just a bunch of random numbers. There's nothing that you
Kind of like a hash, or
it's basically just a hash of some secret. It actually is also a function of some, in practice, at least in what we do, it's this function of some secret values that you only know as the person that is spending the note.
I see.
So in the zero knowledge proof, you prove that you know the secret. You prove it corresponds with the note's public key. And you also use the note, that secret or secret derived from it, in order to compute the nullifier. And then you reveal this outside of the zero knowledge proof. So you can sort of see this as like the boundary of what is visible to the public versus private in the zero knowledge proof would be something like this. Except this nullifier, sort of whatever. Anyway, so all the nodes on the network store these nullifiers in some table or something, and whenever someone spends some money and puts one of these proofs out, and these nullifiers get exposed, you just go through and make sure in this list that the nullifier hasn't been seen before, because otherwise you're trying to spend the money.
So the nullifier is public. It's all that thing's all public.
Yeah. So let's see what else. I mean, it's pretty simple the way it works. Yeah, go ahead.
Yeah. So maybe before we dive into the kind of technical details of how this stuff works, can you just walk us through how a transaction works from a user perspective? Like if user A wants to send to user B some tokens, how that works.
So how the transaction looks, maybe.
Yeah.
Something like that.
Yeah.
Okay. Well, I guess it looks something like this. So we have Alice and Bob. And Bob sends, at least this is the way it works currently, Bob sends an address. And for our purposes, that's just a public key, basically. They send some PK. Good enough. Alice takes that PK and creates, I'll go through some of what Alice does because of symmetry later. But anyway, Alice will create this node object that I was talking about for the funds that they want to give to Bob, and the node obviously contains this PK value, this row value, and obviously the value that they want to send. So Alice wants to send Bob 5 Zec or something like that. Alice also picks some random number. So here's the node commitment. Alice also, this value sort of gets exposed. Sort of in the way that Zcash currently works, the value gets exposed as some homomorphic commitment to the value. So VG R prime H or something like that. This is a Peterson commitment to the value. We can use that to make sure that the balance is correct inside the transaction. So this is what we would call an output inside of the transaction in the Bitcoin model.
Okay.
There's this commitment, and this commitment becomes public. This is public, and we have a zero knowledge proof that takes all these commitments, but also all these spend objects. So these are all the spends. These are all the outputs, and the spends obviously have the thing that I was referring to, the nullifiers. So there'll be multiple different nullifiers, but also there will be more of these encoded, encrypted values of VN1, VN2 that behave like this V value that get exposed publicly as well, and then we check to make sure they're balanced.
So the V is separate from the commitment, or V is the commitment.
V is part of the node, which is part of committed to.
Okay.
We expose V because we're going to have multiple outputs and multiple spends in a transaction. We need to make sure that the sum of the spends minus the sum of the outputs is 0, or the residual fee, whatever.
I see.
So we end up just adding all these together and then adding and subtracting all these, and we get some homomorphic commitment to the balanced version of the value. And then using a Schnorr signature or something on the outside, you prove that that you know the key, that you know this H or whatever, and whatever, and that it's balanced. So the magic in Zcash is to demonstrate knowledge of this commitment, or sorry, well, you have to do that, but also knowledge of the commitments that you're spending. There's not only so much space on the whiteboard, especially when I write so large. Anyway, you have to prove that one of these commitments that you're spending, the corresponding with one of these nullifiers, exists inside the accumulator, the node accumulator. That's pretty easy if the node accumulator is something simple like a Merkle tree. And so you just prove you have an authentication path into it. And there's this other thing that we call an anchor. It's not that important, but basically it's just some previous Merkle tree root of the accumulator, usually a recent one. As the network just says that certain anchors are valid because they've been at block boundaries. We check the current root of the accumulator and add it to a list of valid anchors. And the anchor is the root that all of our spends use as a reference in order to prove authentication pass. So in the zero knowledge proof we're proving, we know authentication pass into the tree to commitments that look like this. We know the randomness. We know we don't necessarily know the secret key, but for our purposes, is good enough. And so on and so on, and then we also prove that we know that this nullifier and that we computed it correctly and we exposed it as part of the spends. As part of the outputs, we prove that we've constructed an output with a value. The zero knowledge proof doesn't care, well, public key we put it send. I know our recipient will care when they get the money, but they don't care about that. We don't. The zero knowledge proof doesn't really care about the randomness who we picked or any of this other stuff. So in a zero knowledge proof for proving is we constructed commitments with the values that we want, and then we expose the homomorphic commitments to the values, and those are exposed publicly. The commitment itself is also exposed publicly. We current it to the commitment creatively, and then the network will do the two things that it needs to do. It checks, well, three things. It checks the proof, but then it also checks, but it checks to make sure the anchor is valid. So the accumulator that's used inside the spends is valid. It then checks to make sure that these nullifiers that are exposed are actually that haven't been used before in a previous transaction. And then it takes this commitment and then it adds it to the node accumulator.
Yep.
And boom, that's plus or minus some extra cryptographic derivation, key structures, and things like that to prevent certain kinds of attacks. And for defense in depth against other kinds of attacks, we add much of the complexity to it that's well justified, and you get mostly what our current protocol is. Actually, what our protocol has been really for the last 10 years, but we've changed it over time and just, tried to make it more robust or tried to adapt to new proving systems or whatever. So, pretty much it. That's the structure of a payment that uses the zero cash model.
Yep.
For the most part.
Yeah, it sounds great. So just coming back to how the transaction actually works. So basically, Bob sends this address or this public key to Alice, and then what does Alice do after?
So Alice creates this transaction that I just described the manner. It gets mined. Now, one thing that happens that I overlook, because I'm getting ahead of myself a little bit, is that this transaction doesn't just contain the nullifiers and the commitment and everything else. It also contains the ciphertext. Currently, this is actually a problem, but I intend to help fix. But it contains a ciphertext that's encrypted. It's sending the details about the node, like this row and this R value and the V and all the rest of this stuff, to encrypted to the public key, to Bob's public key.
Is it encrypted by Bob's public key?
Yeah, it's using a Diffie-Hellman key exchange to create it using a OP and all that stuff. And so, it contains an EPK and an ephemeral public key that's used for the exchange because it's just the one-directional communication. And it gets mined. Bob scans the entire blockchain and looks at every single... Bob scans all the transactions, looks through ciphertext, attempts to decrypt all of them, will fail for most of them, except sometimes it'll succeed. And when it does, it will take and try to check to make sure that it was actually a correct commitment to those being sent to them, some value that they can spend. And if it is, they'll be able to reconstruct the commitment using the information in the ciphertext. And then they know a authentication path into the node accumulator for that commitment, and then they could spend the money later. So
I see.
To somebody else, and then this diagram just completes over and over.
I see. Does it mean in order to transact between, let's say Alex wants to transact with Bob, they first need to establish connection between them? It's a protocol. They need to there needs to be a kind of actual peer-to-peer connection being established.
So I wouldn't mind if that were the case. However, so there is some sort of channel. Obviously, Bob needs to communicate and address to Alice. The manner in which the channel is established is up for grabs. For example, let's say Alice wants to send Bob some money, but Bob never gives Alice an address.
Yep.
Alice could do all this on behalf of Bob, and give Bob the information that Bob needs in order to spend the money. Like create a secret key for Bob, all the rest of this stuff, and do everything, and then create the transaction and send Bob the money. Alex could steal the money if Alice wanted. Alice created the money. Alice could give this blob to Bob on a different on some channel in which and so the direction in which the flow in which some of this stuff happens can depend. But yes, there needs to be some way for Alice to communicate to Bob or Bob to communicate to Alice. Either a public key or here's how to contact me so that we can establish a secure channel so that we can collaborate, make a transaction, and then here's the information you need to spend the money, send it before I do. Or there needs to be some channel,
Yeah, and it both Amazon law needs to like locally maintain the nullifier. So well, in this hollow here where Alice sends the money, once Alice sends the money, Alice doesn't really care. Sure. The nullifier Bob will. Bob needs to carry the nullifier appears on the blockchain. I guess under one is there stole there's public key or secret key or whatever.
So yeah, Bob needs to know what the nullifier is in a simple model. Bob just needs to know what it is and prove it and reveal it, and then hope that they didn't get hacked and steal their money and reveal a nullifier. Now, in the glorious future, we might have a different kind of protocol in which Bob proves that the nullifier that they have for the note they're spending isn't in the spend accumulator, or at least assist in demonstrating such a thing. So they would need to maintain and really care about their nullifier a little bit more than just revealing it and letting the consensus take care of the job of making sure it's on the spend accumulator. That's where some of the scalability stuff might come.
Right, but in order for Bob to be really sure, like he cannot just like trust some like RPC node telling him what the nullifiers are. He probably needs to like run like a kind of a light node that actually tracks all the nullifiers that appear on chain.
I mean, honestly, I don't think so. If Bob wants to, if Bob is, yeah. Well, I mean, obviously, if you ask the server and you say, hey, "Here's a nullifier," has it been used before? The nullifier or the server can give you evidence that it was. You show you the transaction that was mined and say, "Here's the nullifier. It's public." So, but in practice, if Bob has their private key, then nobody else has that. Has the inability to create a transaction with that nullifier. There's no way. So as long as Bob hasn't lost custody of their keys, and they don't have to worry about someone. The hell.
I see what's there.
They need this authentication graph into the tree, and as time goes on, more commitments are being added to the tree, and you need to advance the frontier of the tree, your authentication class as time goes on. Otherwise, when you reveal, otherwise we'll spend the money. The anchor you're using is too old of a version of the accumulator that doesn't include these nodes, and so now your transaction isn't quite as indistinguishable as it could be, because you've basically told everybody that these nodes aren't the ones that you should. In practice, it would require you use quite an old accumulator for it really to matter, but it might matter for different kinds of attacks. So using a very recent version of the accumulator guarantees that you have some pretty strong privacy guarantees. So maintaining this witness requires you either to scan the blockchain as time goes on and get every single commitment that gets added, and then use that in order to update your witness, or you can rely on your own server to provably. They can do this without G. Yeah, they can give you these sort of deltas, or you might call them bridges or whatever. Just the information you do, the water, make them out of information actually, in order to take any witness that has advanced to one part of the one state of the accumulator to any future state. It can be done.
But that's assuming you trust the blob. You like, because like, I mean, you need to indeed. I actually like the root of the thing is in the blob, right? So I need to like wait the process that the blob is authentic.
Yeah, I suppose. Yeah, this all assumes definitely that the consensus is established.
Well, no. Other like even like let's say the chain is like all right, then you asking the server for the like latest block that contains the root, but then what if it give you a bogus block?
Right. Okay. Yeah. Again, another we definitely assume that whatever information we're getting out, like if we're a light type, for example, then we're assuming the server we're talking to isn't lying to. Now we're not really assuming that for privacy reasons, because the worst case scenario is that you're just screwing that you're spending a noggin and familiarity doesn't exist. It's not validate. It's not about is you don't sure feel anything to sure is that interesting, I think. But if you're full node on the network and you're validating everything, assuming you're checking the consensus and everything, you'll never get information about the changes in the node accumulator that you would be able to trust.
And then okay, yeah, that sounds good. Can you talk a bit about the separation between the shielded irises and the transparent type?
Yeah, so the reason why transparent addresses exist at all in Zcash is because for legacy reasons. When we launched Zcash a long time ago, and back then and even to this day, it's very difficult to convince people to use the private version of it because of stupid regulatory things and whatever. And so we had these transparent addresses at the beginning. It also allowed people to use Zcash and learn all this stuff. And people who did want to use this stuff, which over time would make easier and easier, and you don't have to care about all its crap. You just use the very simple things on your phone that send payments just as though if you're sending transparent transactions. But if you wanted to just use Bitcoin style transparent transactions, you could. So we had to have some mixture of the two. It's actually quite simple. In addition to all this shielded stuff, again, we have these homomorphic commitments that reveal the value. Well, I mean, at some point, we have to prove that there's Dallas to the value. That's easy to do. You just reveal this randomness, and then you do a Schnorr signature with the value, and then you use that as a fee or whatever. If transparent addresses or stuff are being sent around, inputs and outputs, just like in Bitcoin, really simple. Now you just have public values that are inputs, outputs. Obviously, just like in Bitcoin, there's some TXID, an index, and it's strip LQ, script sig, etc. And you do all the same stuff, and the value is known to the consensus, and so the consensus can add the value to this and make sure it's balanced. That way, I really truly simply, it lives in the same transaction.
I see. It's the same structure except that there is some of this homomorphic commitment it has there, so what even there. I see. Okay. And variation makes it easy to move between shielded and the transparent.
Yeah, it does, and that also means that we know how much money should be shielded at any given time. So, for example, if there is a bug or sound is probable to SNARK or some other issue, which there has been in the past in Zcash, then if somebody were to exploit it, they can't take more money out of where this sort of black hole universe where all the money goes and lives in this shielded, what we call a shielded pool. They can't take the money out its transparent addresses or into a different shielded pool without passing it through what we call turnstile, which is just sort of it happens implicitly just by the fact that the values have to be revealed in order to relate them to quality values in the transparent transactions, or in order to transmit value from one shielded pool to the other during an interstitial period. We have, in the past, maintained the ability to see the value that passes from one pool to another if we change the protocol mechanism. They don't speak the same language. We expose the value on one protocol, and then you either go to transparent or you go to some other shielded protocol, and you can see it and you keep track of much value. So we use that as sort of a way to hedge against the risk of catastrophic failure. Hopefully, to a big extent,
Yeah, makes sense. And I also heard that the transparent addresses and the serial address actually use different keys, right? One is scientific 61, the other is the AKDSIC.
So the address is, so like this address that Bob is this is a shielded address. it contains a key. In sapling, it contains a key off a different elliptic curve called Jumja, which just happens to be an elliptic curve that's more efficient to do stuff inside of the zero knowledge proof for the zero knowledge proofs that we used. Is in sapling, is the same thing with the newer version of shielded payments in our system Orchard. It's just it's a public key on an elliptic curve that just so happens to be efficient to do. I say with the SNARKs that we were using, the zero knowledge proofs that we were using for transactions in sapling and Orchard, it wasn't efficient for us to do SEC-256 Scalability cheats. Or at least, I mean, there's some ideas there, but it wasn't efficient for us to do that, so we never bothered to do that. We just use whatever elliptic curves we could find or create that satisfy our security needs and efficiency needs. So that's the reason why Transparent stopped uses a different elliptic curve, different anything. For the signatures in this case, we also use the elliptic curve. This isn't done in Bitcoin, but we use the elliptic curve for Diffie Hellman key exchange. Right. So to do these secret tests, you don't need to do that. There's no secret. That's pretty cool. I mean, you have hashes of the scripts, pub key, or the scripts that are used to validate the transactions, but other than that, everything's pub.
Okay, I guess maybe then it should segue to talk a bit about the black box, right? The magic that's happening behind the scenes. Can you talk a bit about the SNARKs that was used on account how that's evolved over the years?
Yeah. So in the original launch of Zcash, we so this was back in 2016 or roughly.
You can do that so for you.
All right, while you guys are racing, I'm going to do one quick thing.
Yeah.
All right, so in the original launch of Zcash, we used a SNARK that had just came out not too long before, called VCQB 13 or 14, I forget what it was. It was around that time. I don't remember what year it's called. And this was based off a SNARK that called Pinocchio. I think it's called Pinocchio. I think that's what you get. Pinocchio was one of the first practical ZK SNARKs that came out, requiring some trust setup, is a cryptography and all that. So the VCTV 13 or 14, I think it was 14. Anyway, so the authors of VCTV 14, I think all of them were ended up creating Osmos as Zcash, the original design of Pix. They kind of teamed up with some other academics to work on the Zcash paper. Required parents. So you can only use elliptic curves for which the sort of decidual Diffie Hellman problem is deliberately made really difficult. Required setups, or it is deliberately made really easy. Trusted setups, which there's some ways you can use pairs trusted setups to do cool things, but most of the time they come hand in hand.
Yeah. So, of which curve that was?
This was the same curve that's used in in Ethereum. Say, well, or one of the first that's used in Ethereum. The anti-2 curve, and so we created a start on this, and it was really slow. It required, like on most consumer desktops, it would require at least around 40 seconds in order to create proof. Totally impractical. But this was the beginning of when this. We had launched this only a couple years after this paper had been published. We were the first people to deploy SNARKs for the general zero knowledge proofs at all and ever. So fast forward, we do some research and we figure out that we're going to do a new version of the protocol called Tally. And the goal of sapling was make the SNARKs maps, or at least make them a lot faster than they are. And we're in fact, make them so fast and so efficient create that you can make them on your phone. To do this, we built our zero-less Bruce law cross 16, which had also adjusting out. So this is 7 was 2018. Okay, so we implemented this using a new elliptic curve, less 1231, which is also used in the turning out. And we're the ones that came up with that one. I guess the authors of the paper we were based off in Zcash, the B2 to T4 curve. I think it was probably either around Tremere or Mid-Reserve or something like that. I mean, that curve, I don't know. They just made it safe curve. Good for us, so they found something. What's important about these curves is that they are just pairing friendly curves. They have to pass certain structures in that make it efficient for you to do multi-pi evaluation and interpolation the polynomial with a large whole large degree polynomials that code the circuit and things like that. So they have redesigned so that they're friendly to FFTs that they carry. That's what we call it at the time. There's ways to avoid that now. So Crowd16 uses this new protocol. It also uses so that it's important to distinguish this curve is what's used for the SNARKs, but underneath it lives the cryptographic predicate that are efficient to evaluate or have used inside of this. The circuits that are built over the scalar field of get 254. We use involved is SHA-256 compression function. When we did sampling, we use BL sub 31 and we created a curve called Gemma. It's just basically a twisted average curve that we use. That's it's very similar to ED2.5 and very
Yeah. One of the things that cross 16 is very fast, but it has a problem which is that requires per circuit trusted step out.
Yep. So it's no different than UCDB14. Per circuit setups absolutely does. But one of the things we did for sampling is that we realized that unlike in the original ones, Zcash does we had created a multi-party computation to do this trusted setup, so that there were 6 people and they collaborated to start parameters, and as long as one of them is on SDRs the parameters are used, we needed to scale that to much larger people. Zcash had launched already. People wanted to be more certain the setup was done correctly. The per circuit setup thing was kind of a pain because it means that you start over and we find change the surface, which sucks. And we started working on addressing that later on. One of the other things is that the setup for this was small number of people. And so the reason why is because the structure of the setup just didn't allow people to jump in, contribute, leave. They had to jump in, contribute, just based on the way the protocol worked at the time. Contribute and then stay around for the next round, which is the polynomials that are used in this original protocol. There's multivariate polynomials that the structure encodes the circuit, and so the only practical way of doing the trusted setup required you to do rounds for every single layer of the polynomial, basically. In Crowd16, so we need to do this step. We weren't going to be able to avoid at the time for circuit setups, but we've at least scaled to origin of people. This is something I worked on where we created a setup which allowed us to do an open-ended setup. And so what we did is we broke Crowd16 out into phase 1 and a phase 2. Phase 1 is not circuit specific.
I see.
And it can run on its own for like indefinitely. At some point we did cut it off because there's only so much we can do. And then at the point that we do cut it off, we go to phase 2, which is circuit specific. And in phase 2, we take the stuff that was created in phase 1, we encode our circuit for the protocol, and then we do a setup. And again, it's open-ended, and it could go on for as long as we could tolerate it. And we stop it at some point and use those for the setup. It is per circuit in a sense because it's phase 2, but the phase 1 would be reused up or you do a different phase 2. So this was sort of a way to make the setup more trustworthy, but didn't quite exactly solve the problem with per circuit setups. And also main trust setups and setups kind of sucked we can avoid. Yes. So the next year, so this is about 2019, I think late 2019. Or no, that's early 2019. Or maybe like 2018, I don't know, forget. I started working on this paper called SNARK. And we had come up with a way to avoid per circuit setups by breaking apart the similarity, the two pieces. One's a polynomial connect scheme or some pattern, and the other is some sort of, we didn't call it this, but it was actually for our purposes, just some protocol that it uses the polynomial commitment scheme in order to demonstrate something. We called it polynomial, or wait, sorry, liking interactive. Yeah, it's IOQ. I have bring that there. I sure work. Yeah, polynomial. PIO.
Okay, yeah. I think that has actually become the paradigm that he will be using for the years to come.
Yeah, that set the stage for all the rest of the week. We sort of broke that up, and we didn't really study formally what was needed for either of the pieces. But we broke them up, and that allowed people to work on more efficient polynomial commitment zones and more efficient BIRPs separately, and then also formalized it, and sort of it led to this explosion. They put Marlin and Plonk and everything, but they didn't require per circuit setups. Everything was just a bunch of unknowns, but everything and the prayers. So that was Sprout Satellite, and then Orchard, which Dad only knows what year that was. I think it was like 2022 or something. I don't know. I don't remember anywhere. Orchard was the new version of the shielded protocol. This didn't require a trusted setup. This did use, I would say, SNARK. You use inter-product Arduino-based SNARK. Inter-product argument plus something that's based on Plonk. I'm sorry, I said Plonk. As it's described, is the protocol that uses a pairing from the thing, but it is a general protocol for using polynomial commitment to be next. Product parameters just doesn't work very close. Yes, I don't. Yeah.
But the downside is has longer proofs. Right?
I wouldn't say it is longer. The proofs are logarithmic in the size of the circuit. That's no big deal. It's actually pretty competitive, and it was constant side. The problem is the verification time.
The verification,
and it's definitely longer. A lot longer. It's so much longer that we can't deploy IP-based SNARKs of any significance inside of something like Ethereum because to compete with the cost of size or cost of time, verification of pairing-based SNARK, it's not gonna work. The curve we use for this, we actually use several curves. We call them pasta curves. Because they form a cycle with each other. We use one of the curves for the actual SNARK itself, and then the other part of the cycle of the curves is used for the the public keys and all that kind of stuff inside the protocol. And because each one of those curves has as its scalar field, base field of the other curve, you can use cycles of elliptic curves to do proof carrying for first and stuff. So in the meantime, in between Sapling and Orchard, we started really focusing on cryptographic primitives, protocol changes, and research in order to make recursive proofs classical. Because at the time, before or just after Sapling, when we started doing this, there wasn't any way to do recursive proofs, subproofs, so on, proof carrying data in a more general sense, without doing without using these pairings and all this other stuff, because the only way we knew how to do recursive proofs at the time is you take the verifier, do proof, and you encode you can ensure get inside to chat. Of course, that only really works if somehow the search, the verification is already converted to CSI, it was open way to sublayers, and we are able to avoid that using some tricks that we came up in the Halo paper. And Halo introduced this concept which has been sort of adapted and formalized in different ways. Some people call it accumulation schemes, or people call it full win. Yeah, whatever. The idea is to take problems that are similar to each other and probably under an academic come up with a way to rephrase that in terms of accumulators or folding it, whatever you want to do. And so that's led to an explosion of papers where people come up with ways to do recursion in without trusted setups, more efficiently with trusted setups, and all sorts of crazy stuff. So lattice-based stuff comes these days as well. Yep. So that's the reason why we use pasta curves in the worship protocol, because we're kind of setting the stage. At least what we were trying to do is use these Kurt cycles together with the idea of in Halo. Back towards it's 20-ish or something like that, late 2019. And we were meant to take the worship protocol and make it more efficient by using our first proofs. And so we'd already have as this curve site one everything. Now, time has passed, and so I'm not entirely sure that we use for recursion in the future, right? We might ditch those curves and do something else. I don't know yet. Yeah, but that was the sort of what we're doing for.
Yeah, so good. I think we're almost on my plan. Any, last things that you want to talk about regarding the kind for?
Well, anyway, so in the protocol that I read before, Bob sends an address to Alice. Alice creates a transaction, gets the money. Transaction creates a cipher there, has the same effects, and then Bob has to scan all the whole text, not correct it, but it doesn't scale. This says number of users and uses it, and the payments increase. Bob can do that. There are other payment flows which involve tells about talking to each other in some way, or an existing channel or a new channel or whatever, in order to do this exchange of information without having to put it on a chain, so that Alice gives Bob the information in order to create the witness for the spend they'll have here. So they can do that. In the existing protocol, it's really easy to update your witnesses into update your authentication path in the merge tree using the bridges I was talking about earlier. So that's not a scalability problem. This is scalability around the scanning, or just sort of what we call it, at least, or what I call it, is the scanning goal. That's avoided by changing the way the payment flow works. The other problem is, and probably the main issue, is the nullifiers. Every single time some money is spent on the system, these nullifiers have to be disclosed, and we could need some evidence in order for the consensus rules to establish that you are cheating and you are forging money, that you're double spending. Something or some combination of things need to make sure that the nullifiers are unique and haven't been used before. We need some sort of non-membership proof in conjunction with the ability of the consensus rules and the ability of the system to check to make sure that these nullifiers are being reused.
Why don't you need a proof? But for all the full node, they do have all non-fire for you. You can't just do look up to see it.
Exactly. Now, so what we'd like to avoid is all the full nodes having to keep the players around. That becomes impractical. That's how it was on it. It says war. So we need to horizontally scale the actual storage up, and storage of these nullifiers, and the act of actually checking that the nullifiers have been reused. You need to horizontally scale that somehow. You can use sharding to do that. There's other things that you can do. Potentially, you can do non-membership proofs into versions of the accumulator, older versions of the accumulator, to help the network. And if you're required to do that up to a certain threshold, then the network can start forgetting old versions of all values of the nullifiers, because then users of the system can just demonstrate non-membership proofs of the old versions of the accumulator. And as long as those are valid and the nullifiers don't repeat in more recent versions, then you know that there's no duplicate nullifiers. And so that's sort of the direction we're moving. I'm moving anyway toward in making Zcash scalable. And so this is sort of the so being able to take a non-membership proof and then update it to a new version as the spend, what do I call it, a spend accumulator or something like that, and it's with additional nullifiers in it, being able to do that update, or to be able to, at the very least, be able to get a non-membership proof from somebody that you can use in order to create a transaction, is sort of a problem called the syncing problem. And solving both of these problems pretty much solves most of the scalability bottlenecks in a private payment model like ours. It's just a matter of being clever about how the communication channel is used in order to perform the original payment to scan or receive the note that you want to be able to spend, and then maintaining your witnesses, which is your authentication path into the Merkle tree, or to whatever accumulator you're using, in order to prove that you have a note, and also prove that you have spent a previous. However that works, and there's different ways of doing it. However it works, that is the syncing problem. And so as solving these two problems, that's scalability challenges for Zcash in a nutshell, basically.
Yeah, okay. That sounds very exciting, and looking forward to a future where Zcash solve both of those problems.
Yeah, me too.
Absolutely. Okay, thanks, Sean, for the whiteboard session.